Welcome, everybody. Great to see so many people here late in the day. I know it's been a long day for a lot of us. Hope it's gone well for you guys. We have a very interesting talk today, focused on machine learning in production and how to architect for scale. So I am a member of the Solutions Architect team in Google Cloud. My role is to basically help Google Cloud customers use machine learning technology. I turn that into solutions that ultimately get published on our cloud.google.com site. This is a very, very near and dear topic to me. By the way, I'm going to be joined later on stage by a couple colleagues, Drew Hoden and Kevin Tsai. So I'll be bringing them up later to talk about some interesting topics related to ML in production and how you scale it. So let's take a look at the agenda. First, we're going to talk about what we mean by scale in the context of machine learning, because there are some specific aspects with respect to scaling that apply to machine learning that don't apply to other domains. We're going to give a very high-level overview of architecture for machine learning on GCP, different ways that you can do it, some components and services that we would typically employ in a ML production system. We're going to talk about Cloud ML Engine, one of the key services that we have on Google Cloud for machine learning in production and elsewhere. We're going to talk about how to use Kubernetes for ML. And that's where my colleague Drew is going to come up and give you an overview of that. And then we're going to focus and drill down on scaling in the context of training and prediction. So there's a lot of content to get through here. I'm going to try to move fast so that we get through all of it. So let's get started. So I'd like to start with this quote by everybody who has ever tried, namely that doing ML in production is hard. And if you have tried it, you probably are aware of this. So let's talk about what do we mean by scale when we say ML production, scaling, architecting for scale. What do we mean? Well, there's a basic definition for scale in architecture in general on cloud or elsewhere. That, as load increases, we want to maintain availability and response time. I mean, that's kind of a standard definition for scalability that isn't really specific to ML. We want those characteristics to remain within acceptable ranges, right? So as the load increases on predict, then we want to make sure that the latency associated with each prediction stays reasonably constant or doesn't fall outside of a range that would not work for us. But, and again, for training machine learning, we care about things like having the time to convergence that it scales kind of, in a reasonable way with the amount of data that we have, right? So that's something that we don't typically have to concern ourselves with when we're scaling in other production contexts. And then for prediction, we want to make sure that as the model complexity increases, that the latency associated with each request also scales appropriately. That we don't hit some exponential or some wall where suddenly, as our model gets too complex, our prediction latency falls off the cliff. And it's even more complicated than that with machine learning, because you have to worry about machine-specific hardware, machine learning-specific hardware like GPUs and TPUs, right? Those introduce different dynamics into the scaling process. And furthermore, as you know, if you're building machine learning models, we don't just care about performance, in training or production, but also about the process of building machine learning models, right? That has to scale too. In other words, we know that we're going to have to run hundreds, maybe thousands of experiments, and we need a system that allows us to do that at scale. In an efficient way. So that's also a really important thing to pay attention to, right? We need to have a system that allows us to not just scale when we're in production, but scale while we're training our model in the development environment. All right, so let's talk about the architecture landscape for ML in production as it exists today. This is a rapidly changing environment, right? And it's going to be probably a little bit of a different story even 6 months from now. But as it exists today, we have a set of best practices and standard templates or architectures that we would use for deploying ML in production on cloud. So I just want to start by making the point that Google has achieved a scale in the deployment of production machine learning that really probably isn't duplicated anywhere else at any other company in the world, right? So we have proven that it's possible to deploy machine learning models in production at the scale on the order of thousands of models, right? In fact, that graph shows, it doesn't actually go out to 2018, but we're now well over 5,000 models in production, pipelines that are in production doing machine learning that are powering a lot of the services that you see over there on the right. Obviously search, but Drive, Translate, Gmail, Maps, YouTube, and so on, right? So machine learning is critical to all of those services. And all of those services are supported by machine learning pipelines running in Google's own internal cloud. So we figured out how to do it. We had to. Machine learning is really core to Google's business. This is one of the keys, the secrets that we've developed to solve that scaling problem internally at Google. We published this paper last year, so it's no secret. But we have a common architecture that we use to build and deploy our machine learning models at Google called TFX. I mean, you should take lesson number one from that is that having a common architecture that you use to build and deploy and serve your models is critical, right, if you're going to do it at scale. And so we realized that for a long time. We built this TFX common architecture based on the learnings of many, many years of doing this in production. The other point that I want to make about scaling in general, this applies to, particularly to Google Cloud, is that we're going to assume that in this talk, that we're really talking about serverless architecture, right? So it's going to be a lot harder for you to scale if you're worried about individual servers for your training cluster or even your data preprocessing pipeline. And GCP is explicitly designed to leverage serverless architecture for all parts of this pipeline. So we're going to assume that we're talking about serverless. That kind of takes a lot of the stuff off the table with respect to scaling. But serverless architecture is going to be key for scaling. So this is a high-level architecture diagram of TFX. It was present in the paper. There's actually a talk in the TensorFlow Dev Summit that you can go out and find on YouTube that talks about this architecture. Not all of this has been open sourced. There are a few components of TFX that have been open sourced, and we do plan, and we have explicitly announced as such, on open sourcing the entire stack. But it's not all done yet. In particular, we have model evaluation and invalidation. TF model analysis was just open sourced. On the data transformation side, there's TF transform. We've open sourced a serving component as well, TF serving. We actually did that last year. So that, by the way, those components are the same components that Google uses in production for our own internal workloads. So if you use these components, you're basically running on the same code as Google. For each of these architectural components that you would use in a common architecture for machine learning in production, there are GCP services that correspond to those. I'm not going to go through all of them, just in the interest of time. I do want to point out so those are all of the services, the hexagons for GCP that correspond to each of those components. Like I said, I'm not going to go through the whole thing in detail. I do want to point out, again, some of the key components that you would use, not TFX-based, right, but that services on GCP that you would use to solve these problems, right? So for training, ML Engine and GKE, or basically Kubernetes with Kubeflow sitting on top of it, are two of the best answers we have for that. We're going to talk in more detail about each of those later. For tuning, ML Engine offers a hyperparameter tuning service, and if you haven't taken advantage of it, you really should. It's one of the key differentiators for Google and for Google Cloud in the realm of machine learning. In fact, I'm not aware of another cloud service that offers a tuning service like this. This means adjusting all of the knobs on your ML models to optimize their performance. Model evaluation and validation, I mentioned TFX model analysis. It's very critical, actually, so that you can understand how your model is performing across all of your data sets, and if there's a slice of the data, for example, that it's not performing well on. It's also critical for things like explainability in ML, which I would love to talk about more, we won't. But you have to be able to break down different slices of your input data in order to understand how your model is really performing in production. And then finally, as I mentioned, for serving, we have TF serving, which again would typically be deployed on Kubernetes, on GKE, and ML Engine as answers to that. So let's talk a little bit more about Cloud ML Engine. Cloud ML Engine has been out for a while. It's quite robust now. We have a lot of customers using it for all kinds of different workloads. It's a platform as a platform as a service for TensorFlow, but as you know, not just TensorFlow anymore. So you can run XGBoost or scikit-learn on Cloud ML Engine. And again, it basically serves as on-demand infrastructure for machine learning. So you can set up clusters to do your training jobs. You can once you've trained your model, then you can take that same model and deploy it as a cloud endpoint, as a REST endpoint. So you can seamlessly transition from training to prediction. It offers some built-in model version management. And then basically you're still just using TensorFlow, so you could take that model, there's nothing locking you in. You can take that model and download it and run it elsewhere on premise, even on another cloud. For our purposes here, for scalability, the pros of ML Engine are that it's very easy to scale up in terms of asking for more capacity for more workers. You just basically specify that in your training job. And it's also nice that the serving capability is automatic. There's been some recent improvements in things like startup latency and other aspects of serving. We're just about to announce increased capability to use GPUs for Cloud ML Engine. So it's got a number of advantages. The cons, I would say, are associated with using distributed TensorFlow, which is just not easy, no matter how you slice it. Again, we're working on the TensorFlow team to make that easier, but it's still got some gotchas associated with it. We're going to talk a bit more about that later and how you can navigate that. There are some limitations, like limited machine types, which again we're working on resolving. So again, there's some some limitations in this service that make it not ideal for some cases, but it's still quite a very powerful service. With serving, for example, again, ML Engine in terms of scalability, you're not in charge of provisioning the number of machines. There's some knobs and parameters that you can tweak, but essentially it scales according to your load, which is great. All right, for a section on Kubernetes for machine learning, I'm going to bring up my colleague Drew Hoden on the CE/ML specialist team and have him tell you a bit about that.
Awesome. Thank you, Lukman. So for this section, we're going to talk about the best of two worlds that I work with customers quite a lot on. One is Kubernetes and one is machine learning. And look at how Kubernetes can help solve some of the problems totally in open source and across multiple clouds. So ML in production, for those of us that have tried or have done ML in production, we know that we care about these three things: composability, portability, and scalability. And let's talk about each of those. First is composability. When you solve an ML problem on your laptop, it's easy to solve some problems maybe on Kaggle on your laptop, small to medium data set with it's kind of what I call toy machine learning. You solve the problem, maybe you won the competition, but that's not the same as taking your solution, scaling it, and making it worthwhile and frankly, worth the money and the effort for the enterprise. There's a lot of things that come after that. Not just the tuning and building the model, but deploying it at scale, refreshing your model every week, day, 15 minutes if you have cold start problems, A/B testing, model evaluation, and serving at scale, right? The reality is that to do each of these different portions of the pipeline, there's different systems. We have data ingestion. So, where is the data coming from? Is it real time? Is it streaming? Is it from a variety of different systems? Who's putting it all together in a data lake? We have our data analysis and validation. So this is exploring the data, understanding what we can actually model or glean from the data. Then we actually have the model building itself, the training, the hyperparameter tuning, and lastly, the serving at scale, keeping the model fresh. Now in practice, these are often different people, if not different entire teams, doing this at scale in production, right? So there's very different skill sets, very different systems. And it makes sense, right? These are very different problems. One of the promises of ML is that we sort of unify all of the, we unify a lot of our data. We apply an algorithm to a business problem. We do it in real time. Now, this is great, but when you have lots of teams involved, lots of systems involved, it can become more difficult to scale. Every time you deploy a model, do you have to get every team involved? So we care about composability. Essentially, reusing different pieces from each stage with sort of limited engagement or friction each time I want to build a model. For example, building a model that can be used by a software engineer in the future on similar data without having to go back to that ML researcher. Now, some of us also care a lot about portability. So just show of hands in the room. Who's using Kubernetes or has explored Kubernetes? A lot of hands, right? That's awesome to see. And these days, definitely the best place to run containers at scale. One of the great things about Kubernetes is you get a similar, the way we've abstracted the compute, you can take your application and move it very easily from your laptop to an on-premise cluster to one of various cloud providers. And this is something very important to lots and lots of organizations. We hear this again and again. Also, we have great primitives in Kubernetes with dealing with things like this. So Joe Beda, one of the co-founders of Kubernetes, says, the way I think about it, every difference between dev, stage, and production will eventually result in an outage. And it's very easy in Kubernetes, at least easier than in a lot of other systems, of treating things like dev, staging, and prod as sort of first-class citizens that the app understands and helps to limit the problems you're going to face. So let's talk about portability with machine learning. Now, because machine learning is such a compute and performance-intensive application, we actually care a lot about all the different pieces of our system, all the way down to the hardware. But it's not just the hardware, it's up to the drivers. Anyone had problems installing drivers and it takes a long time before you can actually start working on your problem? It can be quite a nightmare. The frameworks, they change very quickly. You know, this is a very rapidly moving space. There's a lot of effort that goes into building the stack on a laptop, getting data training, getting a model working. You're super lucky if it converges right away. But again, this is great for solving a toy ML problem. What happens if I want to scale or I want to deploy this in production? Now I'm dealing with different environments, right? Maybe I have a training rig in the back, you know, cooling the office. Maybe I'm using an on-prem cluster. We have existing significant GPU or CPU investments. Maybe this isn't a cloud provider. We're multiplying the complexity of keeping these environments in sync. You know, it was already hard enough to get the laptop up and running that environment perfect for what we were wanting to do. It gets even more complex. So, pop quiz, what's really good at composability, portability, and scalability? Kubernetes, you got it. Containers in Kubernetes. And guess what? Google runs all of our machine learning on containers. And essentially, you know, Borg, but the influence behind Kubernetes. So this can be done. And we have some great news. Kubernetes today has a lot of great primitives and support for machine learning workloads. We support accelerators in a very easy to use, extensible manner. So GPUs are in beta, TPUs are in alpha. With just one line of, in your Kubernetes manifest, you can request GPUs for your pods. It's really easy to schedule lots of GPUs and bring lots of horsepower to your workloads. The existing controllers in Kubernetes also simplify a lot of the DevOps challenges we face. Now let's remember, the reason we want to use Kubernetes here is we get lots of wins from the infrastructure standpoint, from the repeatability standpoint, and from the DevOps standpoint. We want to apply those wins to our machine learning workloads. Some of the ways that it does this is Kubernetes jobs. So when I create a Kubernetes job, maybe this is a training job, Kubernetes will then go create a pod or multiple pods to try and complete that job. If a node fails, let's say I'm using preemptible nodes or preemptible GPUs, it'll take that job, it'll schedule it somewhere else for me. If I'm using, say, the Tensorflow Estimator API, I'm checkpointing regularly, my job is all of a sudden stateless in a way. Kubernetes will recreate the pod, it'll keep training somewhere else in the data center. We also have Kubernetes deployments, which are great for serving. So you tell Kubernetes what your deployment looks like, where the container is or where the model is, how fast you want to scale it, and it does all the rest for you. As your load increases, Kubernetes will create more pods on your behalf. It also scales. At this point, I think Kubernetes will scale up to 5,000 nodes, and that's increasing quite rapidly. And we also have container-based images for ML workloads. So you don't, in some cases, you don't actually have to build your own containers. You can use an off-the-shelf TensorFlow CPU container, and then there's a GPU container. And if you're comfortable with code control, you can actually just load your code up at runtime. There's benefits to building your own containers, but you don't even need to get started using Kubernetes for ML. So this is great. We have the right primitives. We have the right tools that Kubernetes supports. But a lot of the things I just talked about, if you're a data scientist or machine learning researcher, might not be as familiar to you, right? Maybe you feel like I need to learn about containers, container building, endpoints for serving, persistent volume, scaling, all these things before I can be really effective with machine learning on Kubernetes. We see the promise here. We like that we can get a consistent environment, or we can get a similar environment on-prem to the cloud, but there's a lot of other things we still have to build. So the good news is we have an answer, and that is Kubeflow. So Kubeflow is an open source project whose goal is to make it easy for everyone to learn, deploy, and manage portable, distributed machine learning on Kubernetes. So basically to get all those infrastructure Kubernetes wins, but make it really easy for those that aren't Kubernetes experts. And this is a trend we're seeing more and more in the Kubernetes world, is higher level frameworks that make it really easy to solve a particular problem. So what does Kubeflow get us? It gets us composability. We have a variety of existing popular open source tools. I'll dive into those in a little bit. We use KSonnet for packaging and easily setting up your environment. So all of a sudden, dev, staging, production, laptop are all first-class citizens, and with just a couple commands, you can deploy to each of them the same exact code. It's very portable. Kubeflow is totally open source, using totally open source components, and a lot of those components are cloud-native, Kubernetes-native components. I'll talk about those in just a second. What's great is that the huge community that's built up around Kubernetes is solving your problems so you can focus, your deployment problems, so you can focus on the actual machine learning problem. And lastly, it's scalable, right? TensorFlow already supports CPU, GPU, TPU, distributed. Kubernetes scales like crazy. We can use that power to handle our serving workloads and our training workloads. So what does this look like? And how does this solve this whole mess? Well, for those of you that know, Kubernetes will actually solve a lot of it for you. That's why we're looking at Kubernetes as a solution, right? So I'll kind of go back and forth. Kubernetes will give you a pretty consistent API up to the runtime. So I don't have to worry about this anymore. I've abstracted my compute to a really nice level, and I don't have to worry about keeping it in sync. Now that said, you're still having to worry traditionally about the framework, what my storage is, maybe drivers. Kubeflow, with just a couple commands, can be installed on Minikube on your laptop. Minikube is a local mini Kubernetes cluster running in a VM, but you get the same API as if on your laptop, as if you were in a 5,000 node cluster with thousands of GPUs. A couple commands, you install Kubeflow on your laptop, on your on-premise existing cluster, on various cloud clusters, and now you have a consistent ML-ready environment across wherever you do compute. So what's included in Kubeflow? So we actually just released version 0.2. So we are earlier in the days of Kubeflow, but this is developing very rapidly because customers do want a solution that spans across clouds. For some customers, being totally open source is very important. Running in multiple clouds on-prem is very important. Same reasons we've seen the popularity with Kubernetes in general. What's included today is Jupyter Hub for collaborative and interactive training, a TensorFlow training controller. So now you don't have to tell Kubernetes what a TensorFlow training job looks like or how to do distributed TensorFlow. You just tell it, hey, here's my code, run it distributed. Very similar to how you would do with CloudML Engine. Same thing with serving. You don't have to tell Kubernetes what TensorFlow serving is. You just say, here's my model, go serve it, and auto-scale it. We have Argo for workflows, so creating a consistent pipeline from pre-processing to training, hyperparameter tuning, and validation. Selden Core for complex inference and non-TF models. I want to stress that this is not just for TensorFlow. We have PyTorch and Alpha. We definitely have people running Scikit, XGBoost in Selden Core. You can run whatever frameworks you want. Also in point 2, we released hyperparameter tuning and Ambassador for reverse proxies. So this is a very rapidly moving project. All right, and then for our next section, I'm going to invite Kevin up, or Lukman, for scaling training.
Thanks, Drew. Yeah, so I'm going to have Kevin come up now and talk about scaling training, in particular about the challenges of doing distributed training on GPUs. Thanks, Kevin.
Thanks, Lukman. Okay. One of the very common questions that we get from the community is I had one GPU and I just upgraded my VM to 4 GPUs, but training is just as slow. What's going on, right? If you take a step back and try to think about what you're doing within TensorFlow, you're creating a graph, and then you're executing the graph, right? And by default, if you don't specify where your graph goes and TensorFlow sees one or more GPUs, it'll throw the operations in GPU 0, right? So there's a really nice tool from NVIDIA called NVIDIA SMI. If you run that during training, you'll be able to see how busy your GPUs are. If you run it on multiple GPUs and you see something like this, right, that probably means that you created a graph that only had busyness in GPU 0, right? So that's actually the expected behavior if you don't specify parallelization over multiple GPUs. So let's take a look at a very simple model, right? And we use this to describe what we're trying to do in parallelization. One of the ways to parallelize across multiple GPUs is called data parallelism. And basically what you're doing is you are replicating your entire model across 2 or more GPUs, and then you go ahead and divide up the data coming in into smaller batches. So let's say, for example, if your batch size is 256, and you split it over 2 GPUs, you have 128 go to the GPU 0, 128 go to GPU 1, right? So that's pretty straightforward. The other way of parallelizing is called model parallelism. And typically, you wouldn't use this unless you get to a point where your model is really big, or you're running out of memory and GPUs and so forth, right? And it's actually also possible to put model parallelism and data parallelism together. Now, one of the challenges when we're splitting data into 2 or more GPUs, right, is at the end, you're going to end up with multiple result sets, right? So if you think about the predictions, you started with 256, 128 goes to one side, and 128 goes to the other side. The prediction is actually pretty straightforward. You just concatenate that, right? But gradient's a little bit more complex. So what we normally do with gradients coming from the 2 GPUs, we'll go ahead and average that, all right? And one of the things that we also found at Google is to have the best chance of convergence, what we want to do is we want to do synchronous replication, right? Meaning that we want to be able to, after each batch, you want to calculate the gradient, apply the gradient, update the parameters, and then go to the next batch, right? That's the best performance. But that also means that the gradient averaging becomes a blocking process. So it's very important that we have a very fast method of applying the gradients, right? So one of the ways that we could do that is just go ahead and use the CPU as the consolidation mechanism. So after each batch, the GPUs will each copy the gradients to the CPU, and the CPU will go ahead and average it out, make the update step, and redistribute the gradients, the parameters back across all the GPUs. Now, that's one way to do it. But as you can already kind of see over here, if we increase the number of GPUs, you're going to increase the number of copies that you have to average out, and then that becomes a bottleneck, right? So a more performant way of doing it is to use an all-reduced type of mechanism to go ahead and do the distribution, right? The other advantage of doing an all-reduced type mechanism is that you could take advantage of the very fast NVLink, right? Whereas like if you're going to let the CPU do the consolidation, you have to go through PCIe. So when it comes to machine learning, PCIe is slow, right? Just remember that. Right? PCIe is actually really slow, okay? So if you take a step back, here are the kind of the options, right? If you were to go ahead and choose a distribution strategy or distribution method today, here are kind of like at the high level what you could choose from. So if you have a single server, it's not too hard. A lot of built-in capabilities within TensorFlow and Keras that's available. So ever since 1.5, we have replicate model FN. And within Keras actually had their multi-GPU model strategy even before TensorFlow did. But in both cases, you have to remember that these are CPU bound, right? Meaning that they use the CPU as a consolidation strategy. Whereas in TensorFlow 1.8, we introduced mirrored strategy, which is part of a larger family called distribution strategy. And mirrored strategy currently is single server, but multiple GPUs, and it uses the all-reduced type of mechanism as well. Now, if one server is not good enough, there are also options for multiple servers, right? And so you might have heard Fei talk about TPUs. So TPU is one of the options to go ahead and go very parallel. The other option, there's an open source project called Horvad, put together by a couple of really smart engineers at Uber. So that gives you the ability to scale over multiple servers with multiple GPUs as well. And distribution strategy, again, is going to be offered as a multi-server option as well. Now, one mention is, if you look at the older TensorFlow documentation, there's a mention of parameter server and workers. Because this method is not as effective in coming to convergence compared to the other methods, what we would recommend is that's probably not the first solution that you should look at. Okay, so just want to spend a little time on distribution strategy. So what we realize is a lot of users already have a lot of code that's written, and we want to be able to make it so that you can kind of shoehorn this capability into your code without a lot of changes. So what we've done is we have put this capability into run config. So you specify a distribution strategy, in this case, mirrored strategy, and you would go ahead and put that as one of the parameters within run config, and you create the estimator that way, right? And if you're using Keras, we also support the model to estimator conversion, and within there, you'll go ahead and specify run config as well. Okay. Thanks.
Thank you, Kevin. Thank you. So we heard a lot of really interesting information about how to scale using Kubernetes as a common architecture and Kubeflow. And we also heard some really interesting information about distributing over multiple GPUs. And again, we will, as a company, always continue to support and encourage people to leverage GPUs on our Google Cloud environment. We also, as you know, provide our own hardware acceleration option, TPUs, and so I'm going to talk just a little bit about that as well. TPUs are now at version 1 and 2. Both of those have been deployed in Google Cloud. TPU version 1 was actually deployed internally in Google's infrastructure on Borg. TPU version 2 has been made available to our customers at Google Cloud, and today we announced TPU version 3. Actually, I think we announced that at I/O. But anyway, we're continuing on developing and improving that architecture, and you should expect TPU 3.0 to be launched sometime later this year in cloud. And the way we make this available to our customers on cloud is something called Cloud TPU. It's essentially a service that wraps around TPU resources that live in a pod and make it easy for you to do your training jobs that using TPUs. This is a quick example of sort of what that looks like in code. Essentially, as Kevin mentioned, there's just simple as basically using a TPU estimator instead of a regular estimator. And then there's some other things you have to do to connect to a cloud TPU, but it's designed to be relatively simple to do. And we do have a lot of customers now taking advantage of TPUs. So for certain kinds of workloads, it can be quite effective. Again, this is just an example of another code change that one could use in order to take advantage of TPU. So just using a TPU version of the optimizer. Again, it's not for every problem, right? You need to have enough data and enough need for scale in order to justify the work that you do in order to customize for TPU. So again, situations where you've got very large models with very large batch sizes, the models need to be able to run on TPU, so not all models currently do. Just worth pointing out. We will get there eventually, but even as of today, there are certain operations that would not be supported. So you may have a model that just won't run on TPU. And you don't want to use cloud TPU for very small models or models with lots of branches, or again that use operations that aren't supported. We're going to talk a little bit about input pipeline performance. That's another key aspect of training. Of scaling with respect to training. So the first point I want to make is that if you're not using the TF data API, you should be. All right, this is as of about a year ago or so, basically our recommended architecture for building data pipelines in TensorFlow. Again, there are older methods out there using input queues and so on, but we really strongly recommend that you use this API to specify your data pipelines. But just using this API by itself doesn't necessarily get you there, right? So this is an example of a ResNet 50 dataset API coded simply. I mean, there's nothing wrong with the way this is coded, but you get through this about 150 images per second. And really, you should be able to expect for this ImageNet problem, something over 1,000 images per second. So what is the issue with this code, and what can we do to optimize it? Well, again, the way when you're approaching the optimization of input pipelines, we suggest that you think is like ETL. Basically, separate the process of extracting the data from the storage, transforming that data to prepare it for training, which typically has to happen, and then loading that data into the accelerator. Think of those in distinct phases, because different parts of the infrastructure are going to be dedicated to that. And so if you can segment those processes such that those different pieces of infrastructure are allowed to operate in parallel, then you're going to get much better throughput. So here's an example where the operations are serialized, just at a very high level, with the time going forward, and the extract, transform, and load, and then train steps are all synchronous with each other. Here, and of course, you would see that the various components of the system are going to be idle at any given point in that cycle, right? Your CPU is idle. If your CPU is doing the data transformation, it's idle while it's waiting for the next data set to come through. And similarly, if you're using hardware acceleration in this kind of scheme, you're going to see low GPU utilization, right? That's when you run that NVIDIA SMI tool and you see something like 25 or 40% utilization. It's often because of input pipelining issues. So this is what you want to see instead, where the processes of extraction, transformation, and loading are all parallelized sufficiently such that your training infrastructure, your GPUs or your custom hardware, the utilization is maximized. So again, we don't have time here to talk about all of the tricks of the trade that you use to do this, but just let's note here that the dataset API is really designed to parallelize in the same way that we just discussed. So again, if you parallelize that mapping operation that's expressed here across multiple cores just by adding a parameter to the function call, that's enough to achieve parallelization there. Similarly, and that by itself gets you from 150 images per second to 600. right? But there's more you can do. So you can also parallelize the reading, essentially the extract step. And you can parallelize the prefetch step that basically allows the data set to be queued up so you can feed it faster into the GPU. And with those two changes, just at the same code, again, it's basically the same pipeline, just with some extra parallelization primitives or parameters added to it, we get to over 1,750 images per second. So just the point to make here is that it's very critical to tune your input pipelines, and that can make a huge, huge difference in the way that your training process scales. So we're now going to talk about scaling prediction. This is a number of interesting topics here. We're going to talk about how you optimize your model. There's a tool within TensorFlow that's been around for a while that's not probably widely appreciated called Graph Transform Tool that we would encourage you to make use of to optimize your models for prediction. We're going to talk a little bit about quantization and what that is, why you would care about that, what you'd use that for. TensorFlow Lite, which is a new framework that's specifically targeted to make models run fast on mobile. Actually, it's a framework for quantization on mobile specifically. We're going to talk about TensorRT, which is a great framework from our partners at NVIDIA that makes it really fast to serve models that leverage some of the capabilities of the NVIDIA hardware. And then finally, we're going to touch on some serving optimizations that you can make to TF serving to make serving process go faster. So what is Graph Transform Tool? Well, it's actually present in the TensorFlow code base. It has been since, I think, pre-1.0. And it has a number of operations that are very useful when you're optimizing your graph for serving. So one of the things that you want to do, typically the serving graph there's some components in the training graph that aren't necessary for the serving graph. And GTT tool allows you to strip those unneeded nodes out of your graph just to make it more efficient, make it lighter footprint, and faster for serving. Again, it will do graph optimization, so it'll remove nodes that aren't doing anything, the identity nodes. There's various other nodes that are typically included in the graph that are needed for training that aren't needed for predict. If you use batch normalization, which is another topic that I'd love to have spend some time on, if you're not using batch normalization and you're training a deep neural network, you're not doing it right. You're not following the best practice. You need to use batch normalization. Let's just leave it at that. There's some information out there that you can go find to incorporate that. It's pretty easy to do in TensorFlow. You will find anywhere from 20 to sometimes more % uplift in both training accuracy and speed to convergence just by using batch normalization. It's a best practice. There's no researcher in deep learning that's not using it. It does some pre-calculation that makes batch normalization go faster. So that's another capability of the Graph Transform tool. And several other useful transforms, including the ability to quantize your graph. So what is quantization? Well, it turns out that weights, 32-bit weights, are quite useful for training, but for serving, we can often get away with much lower precision. Like even down to 8-bit weights. Actually, there are folks out there doing 1-bit weights, believe it or not. But certainly, without losing a lot of accuracy, but achieving a huge speed up in serving performance, you can go from 32-bit weights to 8-bit weights. This is a very common practice, particularly again when you're deploying on smaller devices like mobile devices or devices on the edge. It's even more important because model size really matters. So you get a big uplift in both speed and not, sometimes a little bit of trade-off in accuracy, but typically not that much if you do this correctly. TensorFlow has built-in support for quantization. So how does this work? Well, essentially, during your training process, you're computing basically the minimum and maximum value of these parameters, say weights. You're storing that as metadata along with the weight, and that allows you basically to scale the weight from wherever it occupies in its range down to this 8-bit range. And then so you don't just store the weight, you store a minimum and maximum value. And then so it makes the graph a little bit more complicated, but it's much, much faster to do these things with 8-bit values than it is with, there's no loss in performance. You get a little bit extra model complexity, but you get a big increase in performance. So it's relatively straightforward to do this. Again, using the graph transform tool. There's actually another tool in the TensorFlow code base that can be used for quantization called quantized graph, I believe. We recommend that you use this tool. Frankly, I mean, they're both roughly comparable, but graph transform tool allows you to incorporate several of the other transforms that are gonna be useful when you're doing this to a model prior to serving. TensorFlow Lite is worth mentioning here. This was announced at the recent TensorFlow Dev Summit, and it's a framework built into TensorFlow that basically does this quantization process for specified for mobile devices or customized for mobile devices. So this just shows you a graph of the relative gain in performance between the TensorFlow model and a TensorFlow Lite quantized model running on a mobile device. And I would encourage you, if you're interested in running ML on mobile, to check out this talk on the TensorFlow Dev Summit. It's available on YouTube and goes into much more detail about TensorFlow Lite. Finally, I'd like to talk about TensorRT. So our great partners at NVIDIA have basically been working on this problem themselves. How do we optimize inference given a model? And they've also built some quantization capabilities into the hardware. So the V100 chip, for example, includes what are called tensor cores, which are essentially custom hardware components or chip components that are optimized to execute inference on these quantized values. And TensorRT is a library that they provide that has been that they've worked with the TensorFlow team to integrate directly into TensorFlow. And so it's relatively straightforward, and you can get really, really good performance boosts. It's particularly on the chips like the V100 that have specialized hardware to support this. So if you're deploying inference on V100s, you've got to use TensorRT, or else you're giving up something could be on the order of 10x, maybe 20x factors for performance. Finally, I just want to talk a little bit about some optimizations that you can do to TensorFlow serving. And then I think we'll have maybe 2 minutes or so left for questions. I'm amazed that we got through all this. If we don't have time, if there are more questions than we have time for here, then myself and Drew and Kevin are going to be out in the hallway afterwards. So we're fine with you guys approaching us, and we'll answer as many questions that we can out there. All right, so let's talk about optimizing TF serving. Well, there's really one thing you have to care about when you're optimizing TF serving for scale. And it's really important if you're going to do TF serving on GPUs. You won't actually get the benefit of the GPU acceleration unless you do this, which is to optimize the batching. So basically, this means instead of feeding a single predict example through your TF serving pipeline, you batch them together in bunches, and you execute those all in parallel through the pipeline. And there is some tuning of this process. There's a batching guide, TensorFlow serving batching guide that's in the source for TF serving, and I would encourage you, if you're using TF serving at all, that you read this and pay attention to it, because it can make a big difference in the way that your TF serving pipeline performs. Well, that is it. Thank you very much.